In this video, we will use the work-energy theorem to solve the following problem. A pitcher in a baseball game can accelerate a pitch from rest to 95.5 miles per hour. During this acceleration, the ball travels a distance of 2.52 meters in a straight line. The baseball has a mass of 145 grams. We will consider the force the pitcher exerts on the ball to be constant and neglect any spin the ball may have. And we're asked a number of questions. What is the kinetic energy of the ball when the pitcher releases it? How much work does the pitcher do throwing the ball? And what force does the pitcher apply to the ball? Well, the first step in the problem-solving process is always to write out the data that we are given in the problem. So the data we have about the baseball is the following: that its initial velocity is 0. It starts from rest. That its mass is 145 grams, and we must turn that into kilograms. Using our standard unit conversion, we get 0.145 grams. We also must do a unit conversion on the final velocity, which is given to us as 95.5 miles per hour. So we must make the conversion, first turning the miles into meters. There are 1,609 meters in a mile. Then we must turn the hours into seconds. 1 hour is 3,600 seconds, right? And all of that gives us a velocity of 42.46 meters per second. I'm keeping an extra significant digit for this intermediate calculation. The first thing we are asked is, what is the final kinetic energy of the ball when the pitcher releases it? Now, this is a straightforward application of the kinetic energy formula, which is 1/2 times the mass of the ball times the final velocity squared. So 1/2 times 0.145 times 42.46 squared. And we get that the final kinetic energy of the baseball is 130.7 joules. We would report this as 131 joules to 3 significant figures. I'll keep that extra significant figure, however, for future calculations. Next, we are asked, how much work does the pitcher do in throwing the ball? Well, that is an application of the work-energy theorem. The work-energy theorem tells us that the work done is the change in kinetic energy. In other words, the final kinetic energy minus the initial kinetic energy. Well, we know what the final kinetic energy is from the previous calculation. That's going to be 130.7, and the initial kinetic energy, since we start from rest, is going to be 0. So the work done by the pitcher in throwing the ball is 130.7 joules. Again, we would report this as 131 to 3 significant figures. Finally, we are asked, what force does the pitcher apply to the ball? Well, this is a situation where we're going to use the other formula for work, where work is force multiplied by distance multiplied by the cosine of the angle between them. We have already discovered that the work done is 130.7 joules. We need to find the force. The distance is 2.52 meters. And since the force is being applied in the same direction as the motion of the ball, that angle is going to be 0 degrees because the force is in the same direction as motion. Of course, the cosine of 0 is 1. And see, we're left to solve this problem that the force is equal to 130.7 divided by 2.52, and that is 52.1 newtons to 3 significant figures. So we would report that the force the pitcher applies is 52.1 newtons. Now this is, of course, assuming that the force is constant. It's very likely the force is not constant. The pitcher is likely applying more force at the end of the pitch than at the beginning. But if we assume the force is constant, this is how much force would be exerted. There is a way that we can check this by using an alternate means of calculation. We can find the acceleration of the ball using one of our kinematics equations from earlier on. V final squared equals V naught squared plus 2 times A times the displacement. In this case, the final velocity is 42.46 meters per second. The initial velocity is 0, and the displacement is 2.52 meters. So the acceleration is going to be 42.46 squared divided by 2 times 2.52, and that is equal to 359 meters per second squared. A very large acceleration. We can then use Newton's second law to calculate the net force felt by the baseball in this situation by taking the mass of 0.145 kilograms and multiplying by the acceleration of 359 meters per second squared, and that gives us a net force of 52.1 newtons. This should not be a surprising result since the work energy equation is derived from Newton's second law, but it's always good to get a second opinion.